Okay, I am hoping that. Okay, I have two current viewers. So, who are these two people? Okay, and let us first of all start off. Is anyone there? Okay, I am hoping that. Okay, I have two current viewers. So, who are these two people? Okay, let us first of all start off. Is I'm seeing one current viewer. Okay. What's this all about? Okay, I want to go to the different view. Okay, I believe the last time we were looking at. Okay, I need to do something with these speakers. Okay, I believe the last time we were looking at. Is a way. Okay, it says I'm live. Okay. Is there anybody here? Is there anybody here? I'm seeing 2 concurrent viewers. How is that possible? Oh boy. I'm seeing 2 concurrent viewers. How is that possible? Okay, who's King Jungin's Cupcake? Who's that? Oh my goodness, that's Destiny. Okay, okay, Destiny. Alright, so we'll begin now. Okay, so I think the last day I was discussing problems like this. And what we wish to do is to look at the structure of a past paper. So these are the past papers, and I've been going back all the way to 2009. And this is what the past paper looks like. So I'm going back to 2009, and as I told you before, the question papers always look like this. 2009 paper 2 question 1 January, you see the same kind of question. 2009 paper 2, that's May, June, you see. You see, this, you can see what the first question looks like. Okay, similar kind of structure. 2010. If you look at this paper as well, we see the same kind of structure, right? Some kind of computation to show. So a wise place to start would be going through some of the theories of computation. Okay, so we'll start with the laws, the basic laws of mathematics. We'll start with those laws. Okay, so here we go. Now, we know there are 4 basic operations, and the 4 basic operations are, in mathematics we have 4 basic operations. And they are 1, addition, 2, subtraction, 3, multiplication, and 4, division. Now, we have some laws that we must quickly get to be familiar with. There's the law of commutativity. So what we want to do, we want to look at how we use those laws. Now I will start off with everything in arithmetic first. While we work with pure numbers, right? Working with pure numbers. Now I will start off with everything in arithmetic first. While we work with pure numbers. And then I'll go and do things conceptually, where I'll do some algebra. And the algebra really is working with generality or generalizations. So we want to look at pure numbers and see certain kinds of properties, and then we'll come to a conclusion as to whether we can make a generality with it. So if I have 3 items, 1, 2, 3, and I have 5 items, 1, 2, 3, 4, 5, and I put them together, I will have 1, 2, 3, and then next step will be 4, 5, 6, 7, 8. It's 3 and the 5 together give me 8. Now it matters not in which way I group them. If I did this, I add 1, 2, 3, 4, 5 first, and then I bring to it a group of 3. Then in the end, what I will get will be 5, and then you have 3, so you get 6, 7, 8. So what we learn from that is that this is represented by the symbol 3. 3 plus 5 equals 8, and we see that 8, we also see in the second example, that 5 plus 3 gives us 8. So the order doesn't matter, and therefore we can say 3 plus 5 is equal to 5 plus 3. And we find this to be true at all times. It doesn't matter what the number is. If I use 10 and 6, 10 plus 6 equals 6 plus 10. 9 plus 5 is equal to 5 plus 9. And therefore we can make a general conclusion and say, if we are adding numbers, we can say A plus B is equal to B plus A. Right? And as a matter of fact, I'll qualify it a little bit more strongly and write A plus B, 1, 2, 3. That means it's always equal to B plus A. This sign means always equal to. Right? So this is a general conclusion that we have come to, and we can say then this, in this way we can say addition of two numbers or two quantities, whatever they are, gives the same result regardless of the order in which they are done. So addition is commutative. This way we can say addition, so that A plus B is always equal to B plus A. Gives the same result. Okay. Regardless of the order in which they are done. So addition is commutative. Now, let's do something else. Let's look at multiplication now. Multiplication. So that A plus B is always equal to B plus A. I can write, say, 3 times 5. That actually means 3 groups of 5, you could say. 3 groups of 5. Now, let's do something else. And let's take a sketchy look at that. So I have 3 groups of 5. So 1, 2, 3, 4, 5. That's one group of 5. I want to put it together with a next group of 5 and another group of 5. I want to put all them together. 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5. When I count them all, I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. The 3 groups of 5 is equal to 15. 5 groups of 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. No, when I add up all of those, I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we get 5 groups of 3. Is equivalent to 15. What we can see from that, we can see that 3 times 5 is equal to 5 times 3. So, we could say that, generally speaking, right, this was the arithmetic example. So these examples were arithmetic examples here. But algebraically now, the concept, the generality that we observe, what we see then is that A plus B, A times B, is equal to B times A. Let me straighten that. I should rather write A times B is always equal to B times A. The 3 lines represents always equal to. So we say that, that's the case, we say that multiplication is commutative. Now, these results are very important as we develop our algebra. It looks very straightforward, but because of these properties, we can actually justify steps or things that we will do in a problem or in statement of a problem. Okay, so multiplication is commutative, as is addition. Now, very important to know in terms of commutativity, let's look at subtraction. Subtraction. Now, let's take an example in arithmetic again. Arithmetic. I know that 10 subtract 2 will leave me 8. I also know that this will never be equal to 2 subtract 10. Because in this case, the 10 is greater than the 2. But in this case, the 2 is greater than the 10. So the difference cannot be the same. And therefore, just from that as an example, I can see that A minus B, well, let's look at what the numbers are. 10 minus 2 is 8, but we know, but 2 minus 10 is equal to minus 8. If you don't understand that yet, that's quite alright. What we need to know is that 2 take away 10 cannot be the same as 10 take away 2. Okay? So, in this example, we can see that the first minus the second is not the same as the second minus the first. Now, there can be a case made, I can say like for example, 5 take away 5 is equal to 0. And when I change it around, right, then it will be 5 take away 5 equal to 0. Now, I'm going to write the algebraic statement about subtraction and its commutativity. Now I'm going to write now, algebraically now, I can write that a number A minus B will not always be equal to, this sign means always equal to, and I draw a line through it, B take away A. Sometimes they can be equal, but this means I cannot say that it will always be equal. So in this example here, in this first example here, You saw a case where 10 minus 2 is equal to 8, but 2 minus 10 is equal to minus 8. And clearly, a minus b was not equal to b minus a. That's obvious. In this case, however, 5 minus 5 is equal to 0. When I change it around, 5 minus 5 will give me 0. In this case, a happened to be equal to b. Right? What this symbol means, this statement here, this statement is not the same as this statement. This statement and this statement are not the same statements. Don't confuse these two, they are not the same. Okay, they are not the same. As a matter of fact, this statement allows that a minus b may at times be equal to b minus a. This statement is saying a minus b is not always equal to b minus a. Or it's saying a minus b could be equal to b minus a, but not all the time. That's what this one is saying. This one is saying a minus b is not equal to b minus a. Okay? Now, the one I wanted to remember, the one I wanted to remember for commutativity is this one. Don't forget this sign here. Subtraction cannot always be said to be commutative. Okay? It can happen when the two numbers are the same and they get the answer 0. But we're saying that a minus b wouldn't always be equal to b minus a for subtraction. So from the statement, this one here, we say in that statement we say subtraction is not commutative. Right? Here, a minus b happen to be equal to b minus a. Right? But here, a minus b was not equal to b minus a. And therefore, we can conclude from that that subtraction is not commutative. To be commutative, a minus b had to always be equal to b minus a. And that's not the case. Okay? This means something different. So I'm going to remove this now. Right. If a minus b is not always equal to b minus a, subtraction is not commutative. Okay, so I'm going to take a peek at the chat now and see if you understand that. Okay? Okay, nothing hard. Wonderful. Okay. A minus b is not always equal to b minus a, subtraction is not commutative. Okay, so I'm going to take a peek at the chat now and see if you understand that. Okay. Alright, so we continue now. Right, so what we are saying now, subtraction is not commutative. Let's look at division. Well, 10, we're going to division and the commutativity of division. So if I take 10 and divide 10 by 2, I'll get 5. However, if I take 2 and divide that by 10, let's see, that's 2 over 10, 2 into 2, 1, 2 into 10, 5. The answer will be equal to 1/5. I mean, we have one example. Now, there could be a case, yes, there could be a case in this example here. Let's look at this example. In this example, A divided by B is not the same as B divided by A. Okay? Now, there could be a case where that can happen. For example, again, 15 divided by 15 is the first number, the second number is the first number. If you change it around, this 15 will be, 15 is equal to 15 divided by 15. Because in both cases, the answer will be 1. That's true. So in this particular example, in this example here, what we see A divided by B happens to be equal to B divided by A. So it happens only because the two numbers are the same. But if I just speak generally, I cannot say A divided by B will always be equal to B minus A. That can't be made just because of this example here, where I have one example. This example shows 1 over A divided by B is not equal to B minus A. Once you can get one example where A divided by B is not equal to B minus A, you are saying that division, I can conclude from this that A, let me put it in red. I can put now A divided by B will not always be equal to B divided by A. I have a case where it's equal here, but in most cases it's not going to be equal, so we conclude with this statement that A divided by B will not always be equal to B minus A. And that is interpreted as saying that division is not commutative. Now, once you know this, let's proceed now to talk about associativity. Let's talk about associativity. Okay. So, let's break down the big word, associativity. Now, who you associate with affects who you become. So let's just think about something for a while. Associativity. Now, speaking about associativity, we are thinking about you having choices to choose who you wish to speak to. Who you wish to keep as friends and who you wish to keep as colleagues. Okay? Now, or who you give preference to who you interact with. So we're going to look at associativity in terms of different kinds of operations. So, let's take consider three numbers, A, B, and C. Okay, so I have three numbers A, B, and C. Let's look at what happens if you look at multiplication of those numbers. If I am A, for instance, I could decide I can multiply by B first, and then the result of that, multiply with C. So A and B are closely associated, and when they have finish their association, then they will decide to interact with C. Or alternatively, I can say, write them in the same order now. Consider A, B, and C, but this time I choose to let B and C be multiplied first, and then I multiply by A. Here, I have this kind of association, A and B being associated first, the first association, then we lead on to this 1 second. In this case, this is the first association, and then this is the second association. If, when written in order, A times B first, then multiply by C, is equal to A by B by C, B by C being first associated. If the order in which they are associated didn't make a difference with the outcome, we will see the operation is associative. So let's see if this is really the case. So we want to know if this is the case. If this is true, if true, then multiplication is associative. If false, multiplication is not associative. So let's take some numbers now and check that out. Okay? Let's take some numbers and check that out. So 3 times 5 first, multiply by 7. What that works out to be? 3 by 5 is 15, so this works out to be 15 first and then by 7. And 15 by 7 I think will be 105. That's the outcome there. Let's consider what happens if I take 3 this time and multiply this way by the product of 5 by 7. Let's see what answer we get there. Well, 5 by 7 is going to give me 35, so this works out to be 3 times 35. And 3 times 35 will give you 105. Now, this is one case where A times B times C is equal to A times B times C. So A times B, then times C is equal to A times B times C. You see, it works out here. And we could try other numbers if we so desire. For example, I could try 10 by 2 by 0, right? And I can try 10 by 2 first, then multiply by 0. And the answer here will be 0 is equal to 0. So it works here. But we could find for any number of any number. No, I just did a pair of them, but let's look at, so the long and short of it, for all the numbers that you can try, you get A times B times C is equal to A times B times C. Always. So if we do a set of examples, we find that. And therefore we conclude that multiplication is commutative. It's associative, It's associative. It's associative. It doesn't matter in which way those numbers we multiply associate themselves, in which order, the outcome is always going to be the same. So multiplication is associative. No problem there. Okay. Now, I just wrote 3 items there, but the truth be told, if you do some more investigation, we will find that we'll find that A times B times C times D times, right? Doesn't matter how we associate, you can put A by B first and then multiply that by C by D by E. Or you could have taken the C and A by B by brackets around the C by D by E. That order doesn't make a difference because multiplications are associative. They all, when they are associated with each other, and that chain of multiplication will give you the same result. Now these things are very important because again, to go from one line to the next line and to say the line before is equal to the line that's after, you cannot violate these laws of associativity or commutativity. So multiplication is associative because the order in which you do things does not cause problems. Well, addition, let's look at addition now. Looking at addition. Alright, so the question we're asking ourselves, write three numbers in order, A plus B plus C. I can do this first. I want to know if it will be equal to A plus B plus C first. We could try numbers. So let's take a single case. 3 plus 5 plus 12. Oh, no, that will be the same outcome. Is it the same outcome as 3 plus 5 plus 12? Well, 3 plus 5 is 8. And 8 plus 12 will give you 20. This one here, 5 plus 12, that's 3 plus 5 plus 12 is 17 plus 17. And 3 plus 17 is 20. So here we have a case, a single case, where A plus B plus C happens to be equal to A plus B first, then plus C. So you're seeing that. Okay? Now in D, we try as many numbers as possible, we'll always find this to be true. So we try more and more and more examples. We'll find, for all values that we can find, we'll find that A plus B plus C is equal to A plus B plus C. Okay? This means I always, so that is all numbers I can use. It's always true. This is always equal to that. And therefore A plus B plus C is always equal to A plus B plus C. We could then say that addition is commutative. Is associative. I'm sorry. Is associative. Addition is associative. Now, I want to make this very clear. I'm going to combine. Okay. I'll look at subtraction now and division. If I can find one case, let's see. We'll look at subtraction and division. So again, we're going to investigate associativity. In subtraction. And again, for association subtraction to take place, I'm looking for numbers like A, say take away B, take away C. Right? I want to see if the order in which I do that affects the result. For subtraction to be associative, I'm looking to see whether A take away B take away C is always the same as A minus B take away C. So, if this is the case, if true, if it's always true that A minus B minus C is always equal to A minus B minus C, if that is true, then subtraction is associative. True? And imply that subtraction is associative. If, however, this turns out to be false, that is, if I can only get one example where this is not true, if I get one example where A minus B minus C is not equal to A minus B minus C, then the statement that is always true would be a lie, it will be false, and therefore we will say that from that subtraction is not associative. If, however, this turns out to be false, so let's try the numbers. Let's try some numbers. Let's say that is, so we get one example 10 take away 3 take away 5. That's your A, your B, and your C, and I want to see whether, the question is I want to see whether it is equal to, I want to see whether it's equal to 10 take away 3 take away 5. At this juncture, since we haven't done negative numbers yet, let me change this 5 into a 2. Right. So in this case, 10 take away 3 will give me 7 take away 2. And so when I get 3 minus 2 is 1, here I get 10 take away 1. So 7 minus 2, of course, is going to be 5. And 10 minus 1 is 9. So when I ask the question, is 10 minus 3 minus 2 equal to 10 minus 3 minus 10 minus, open brackets, 3 minus 2, close brackets? Here I'm getting 5 and here I'm getting 9. And those two numbers are not the same. So this is false. 5 equal 9 is a false statement. And if it's false, once you get one example that doesn't satisfy, A take away B take away C is equal to A minus B in brackets minus C. Once you can get a single example where it doesn't work out, we know that we cannot say that subtraction is associative as a given. So here we can see that subtraction is not associative. Here you can see very clearly that subtraction is not associative at all. Okay, and therefore we have to be very careful. What this is telling us is we have to be very careful the order in which we do subtraction. We have more license to do all kinds of things when it comes to addition. We can add in any order. And we can multiply in any order. We can do rearrangements and so on in that order. But with subtraction, we cannot do such a thing. Okay? Subtraction is neither commutative nor is it associative. Let's look at division. Okay, let's look at division. So let's see if division is so you can have associativity. So you want to see whether division is associative. That's what we want to see. So if that's the case, what are we questioning? What we wish to see, you want to see if 200, okay, no, we're looking for the situation. If it's associative, if true, then A divided by B divided by C should be equal to A divided by B, take away, divided by C in brackets, sorry. If it is true that division is associative, then it doesn't matter which order I do that string of operations, I should get the same result. So let's use some examples here. If true, this will always be true. So if I can get one example where it is not true, then this statement isn't always true. And if the statement isn't always true, then I say associativity is not present in division. So let's do some numbers now. Let's take an example. If true, that's what happens. But if false, we will say A divided by B divided by C will not always be equal to A divided by B divided by C. Okay? So let's get some examples. Let's take 200 as one example. We're doing a case study here. So I have 200 and divide that by 50 and we'll divide that by 10. Let's put a bracket here. And we want to see whether it will be equal to 200 divided by open brackets 50 divided by 10. But in this case, 200 divided by 50 will be 4. So this will become 4 divided by 10. But in this case, I'll have 200 here, that's being divided by 50 divided by 10 is 5. So 4 divided by 10 is 0.4. And it's 200 divided by 5, the answer here is 40. So here, we are asking our questions, is this true? But the answer obviously is no. And therefore, we have found a single example. If you have found one example where A divided by B, then divided by C, is not equal to A divided by B divided by C. Once you have one instance, then you have to say that the whole operation is not associative. So, I write since A divided by B divided by C is not always equal to A divided by B divided by C. Since they're not always equal, I know that division is not associative. Now, Destiny, this is where you have to start thinking mathematically now. Now, I want to try and combine the associative and the commutative properties. Right? So right now, for addition, right? Addition is commutative. Addition is both commutative and associative. Multiplication is the same. Multiplication is commutative and associative. Subtraction is neither commutative nor associative. And we say division as well is neither commutative nor associative. Okay? Now, as for addition, this is for multiplication. This is the law for subtraction. That is for division. These are very important results. It may not seem so as yet. Whenever I use them in any question, I will justify whatever step I'm making by telling you I'm doing this because of the associativity of multiplication. Whatever. So, what is it saying to me? What does it say to me? If I combine the two, combining the facts So you combine the facts that multiplication is both commutative and associative. You combine those two facts, get an interesting result. Well, I have A times B times C. Okay? I am saying A times B times C, right, can be made to be equal to B times A times C because I use the commutative property. I could turn this around, I could spin it around and get B times A. Since A times B is B times A, then A by B by C is B by A by C. Okay? Also, since it's a bracketed term, I can say by the product, by the associativity, by the product of commutativity now, I can change that around again. So let's just take this off and let's write a nice symbol. Right? I will let this thing here, this circle with 1, let 1, right, be commutative property. And then let 2 be the associative property of whatever operation we're talking about. So we let that number 1 be the commutative property of the operation. So let's look at multiplication quickly. We're going to have multiplication, as we said. I am saying A times B times C has to be equal to B times A times C, and the reason for that is because A times B had to be equal to B times A. So I could have always take this and write this as B times A, and that would be correct. Okay? Right? What to say here, ready? I can erase this and put because of the property number 1. And that's what I'll do. So I can write now, right? Because of property 1. Now, I can come here now. And I can say now, the product of A times B, that product, this will be equal to C multiplied by A times B. And what I'm doing, I'm using this because of property 1. Right? So, this was first here, and I take him and bring him in front, I just change it around, I swing on the order. So C times A times B of 1 is the same thing. And then again I can actually interchange these two because of the commutative property. So be therefore C multiplied by open brackets B times A. You know, so what we see is therefore A times B times C, the outcome will be the same no matter which order we should do. We take A first and then B times C, or we take A first and multiply that by B and then multiply C. Or if you change it around, you'll get now C multiplied by A by B, and so on. You can see, doesn't matter the order. A by B by C is A by B by C, or A times B first then C, or C by A by B, or C by B by A, and so on and so on. Multiplication, being commutative, allows us to interarrange all kinds of things in a term. Okay? Okay, so it's now now getting to 8:15. Okay, so now I want to do something a little different. Okay, I want to basically state what will happen for addition. So for addition, what we find is that A plus B plus C, doesn't matter what much we add it, will be equal to B plus A first. That's when we turn this around commutatively, N plus C. Then because these two could be written commutatively, you can bring the C first in front, C plus B plus A, and then these two could be interchanged in position. That be equal to C plus open brackets A plus B. I mean, see, it doesn't matter the order, whether C, A plus B, C by B by A, B plus A plus C, or A plus B plus C, right? The order doesn't matter. What we get is that A plus B plus C that's equal to A plus B first plus C, because these two are commutative, we can interarrange them. So it doesn't matter the order in which it's written, we get the same result. So we get A plus B plus C is equal to A plus B plus C. That's equal to A plus B plus C in that order. That's equal to, put B first, B plus A plus C in that order, or B plus C plus A in that order, or C plus A plus B in that order, or C plus B plus A in that order. Right? So they make a difference. Whatever she add and so on, they make a difference. None at all. Now the ones you have to worry about and be very careful about are those that involve division and subtraction. So you know off the bat, that since division and subtraction are neither commutative nor associative, then we know for subtraction to be, then we're looking to see if A minus B minus C is the same as A minus B minus C. That's what we want to know. That's the question we want to know. If that is always true. But you know A minus B, let's put some numbers there. Right? If it's not always true, I know subtraction is not either, it's not associative. Right? So let's do that. 17 take away 8 take away 6. This will be 9 take away 6, which will be equal to 3. In this one, I have 17 take away 8 take away 6 here. 8 minus 6 is 2, so is equal to 17 take away 2. That is equal to 15. So, is that true? Obviously not. It's not true. Now, because of this, 17 minus 8 minus 6, because the order which is written vastly affects the outcome. With multiplication and division, the order which you write numbers do not affect the outcome. Right? But with subtraction and division, because the order in which those subtractions take place make a difference, that is, it's associative, you have to be very careful when working sums with a host of computations involving different operations like multiplication and division and so on and so forth. Okay, so looking at subtraction, we see it's not true. So you know that we can't trust that. And we're saying, therefore, when working any sum, one must be careful to carefully look out so therefore when working any sum, one must be careful to look out for subtractions and divisions because they can lend a completely different interpretation Alright? As you see in here, if you have subtractions or divisions, just the order could result in a totally different interpretation. So you have to be careful with those things. Right, so most students have a problem recognizing these things being problematic when they're working with numbers. But when working with symbols, many students have a problem. So, we're saying, when working with symbols in algebra, I am saying to you, A take away B take away C is not going to be the same to A take away B first, then take away C. In algebra, this is an oft repeated error. Right? Now, for the mathematics, not as important as it is for the algebra. That's very important. Okay? Very important. And this is why we have the rules for BODMAS. Now we have something called distributivity we have to discuss. Distributivity. And I'll just tell you what the laws for distributivity is. Multiplication is distributive over addition and subtraction. So let's talk about distributivity now. So talking about this distributivity, right? It has to do some kind of multiplying. So let's say I have A in the B plus C. The operation understood to be outside the bracket here is either a dot, which means multiplication, or is interpreted as A multiplied by B plus C. Okay, so let's do a test and see what exactly are they saying. Let's say I have 2 to be multiplied into 3 plus 5. Well, if I look at the brackets first, that means this is equal to 2 multiplied by 8. And that's equal to 2 by 8, which is 16. Let's look at something else. If I take the 2 and multiply by the 3, and the 2 and multiply by the 5, and I do this and I add them, and I want to see what the result would be. Well, 2 by 3 gives me 6, 2 by 5 will give me 10, and 6 plus 10 gives me the same 16. It seems as though I have a case where I can say 2 into 3 plus 5 is 2 into 3 plus 2 into 5. It seems as though I have a case for that. But indeed, no matter what number we try, right? Let's say I try 5 into 14 plus 2. I'm asking myself whether that's the same as 5 into 14 plus 5 into 2. So I'm going to compare them and see what's the result. 5 by 14 plus 2 is 5 by 16. And 5 by 16 equals 80. This one, 5 by 14 is 70. And 5 by 2 is 10. And 70 plus 10 is equal to 80. Indeed, for all numbers, we can write A into B plus C equal to A. For all numbers, A into B plus C is A, B plus AC. Or we could say is multiplication is distributed over the addition in brackets. So multiplication is distributed and evenly so over the addition. Right? Okay? That allows us, this step here actually justifies what you call factorization, where I can take something like A times B into A plus C and factor out A out of both of them, and so that's A into B plus C. This here is the basis for simple factorization. Okay, as a basis for factorization, I will use later. Okay, and it doesn't matter how many terms are in the bracket. Okay, as a matter of fact, we also find that A we want to see if A into B subtract C. We want to know whether that is always the same as A Alright, I wonder if that also is the case. But let's see. Well, let's take some examples. So I'll take 14, I'll multiply 3, 5 take away 3, yes. I'll deliberately avoid negative numbers for now. I want to see whether that's equal to, interesting fact, 14 by 5, 14 by 3, and subtract that. So 5 minus 3 is 2, so this is actually 14 by 2. And 14 by 2 is 28. 14 by 5 is 70. 14 by 3 is 42. So 70 minus 42 is 28. The same 28 we get here, same 28 we get here. Well, you could try for as many numbers as you like, find it's true. And we say that A into B minus C is equal to A into B, A into C. Again, basis of factorization, going from this form, we're taking out A to be as a factor. Okay? Now we've been pushing a lot. So we know multiplication in both cases is distributed over addition and subtraction. But division, let's see division is distributed. So, we're looking at distributivity and division. Now, we want to see therefore if a number A divided by B plus C. So what kind of division is distributive about that? So let's see. I want to see that's the same as A divided by B plus A divided by C. So let's put some numbers and see that's if it's always the case, sorry, yes. So we could find one example that actually causes two things not to be the same, then automatically know that you cannot say that distributivity, sorry, division is distributive about addition and or subtraction. Right? So let's try some numbers now. Let's say A is 100 and 100 divided by 15 plus 5. Right, so we're asking ourselves 100 divided by 15. 100 divided by 5. And we're asking ourselves, that's the case. 100 divided by 15. Well, 100 divided by 15. Right, we'll come down to 5 into 15, 3, 5 into 100, 20. There's 6 and 2/3. So ask myself then, and this one will got to be 20. And clearly not equal. I get 20 and 3 and 20. Clearly not equal. And therefore, we can automatically conclude that division is not distributive about about addition. I'm sorry. Alright, so we're going to find out what will happen. Distributive division is not distributive about addition. Now, we're going to see division is distributive about subtraction. So let's try that. So I get my pit here. That means I could take, for example, ask myself if 250 divided by 10 take away 5. This is the subtraction. I want to see whether this will be distributed above that. We want to see whether that will be equal to 250 divided by 10 take away 250 divided by 5. So we are assuming that 250 divided by 10 minus 250 divided by 5. Well, let's see what we get there. Well, in this left hand side, I know 10, these are brackets, so I know 10 minus 5 is 5. So as far as I'm concerned, I'll get 250 divided by 5, which will go to be 50. In this case, what I get on this side, 250 divided by 10 will give me 25, obviously. And 250 divided by 5 will be 50. It's 25 minus 50. And 25 minus 50 is minus 25. This number is 50. Clearly not equal? Clearly not equal? So we know for a fact that division is not distributive about subtraction. Division is not distributive about subtraction at all. So what this does, Destiny, it makes certain things illegal in a problem. So what they are saying now is when working problems, what they are saying is if I have, and in symbolic form, in algebraic form, students do it all the time. But if I have, for example, a squared divided by b plus c, to simplify, let's see as an example, what you cannot do, because it's addition here, but this is division, and division is not distributive about subtraction, neither is it distributive about addition. You cannot say, when we're going to sum with algebra, you cannot say this is a squared divided by b plus a squared divided by c. Students do these things all the time. That's the major source of their undoing. So, yes, we know the laws in terms of arithmetic. Of course, we have to apply it in terms of algebra. Okay, so I see we have about 20 minutes again. So, I will try now, therefore now, to explain BODMAS and BOMDAS. Okay? And then I will try to actually explain, when you look in those sums, those number one sums, what you actually see. Okay? Now, let's look at order of operations. Now, in order of operations, if you do a set of operations, you must know the order in which to work them. And the order in which we work them obviously depends on the operations that are present. So, there's an acronym used in primary school, and we used to say something like this. The order of operations must be done in such a way that number one was brackets. Anything in a bracket must be done first, because he has the highest precedence. Bracket. Then secondly, it tells about something called of. The wise teachers will teach BOMDAS and not BODMAS, so you get BOM multi multiplication. That must be done next. Then fourth, division. Then fifth, addition. Right. So we have these 6 here, brackets of multiplication, division, addition, and subtraction. Okay? I need to mention to you again that brackets simply tell us what ought to be done first. And there are some implicit brackets in the problem. Let me tell you, if you see a mixed number written, 1 3/4, if you see 1 3/4 written like that, this actually means a bracket of 1 plus 3/4. That's what it means. Whenever you see a mixed number written like this, you can interpret it as having a bracket in it and adding the whole number part to the fractional part. Okay? Very, very important. So, in many problems, we find ourselves in number problems. The first step being converting mixed numbers into improper fractions. Okay? Because when you write a mixed number, a bracket is understood to be in front of it. Okay? Well, of many men multiply. It literally means multiply. Right? It literally means multiply. And multiplication is multiplication. Right? So division now. Division actually is the multiplication by the reciprocal of the divisor. Addition is what it is. And subtraction is really addition of a negative number. Now, why did I give you this? I gave you this because there's a hierarchy when you're looking problems. There's a hierarchy. Okay? And hierarchy basically starts off with brackets and powers. Right? The hierarchy, the top dog is brackets and powers. After that, on the lower level, we have of multiplication and division. And below that, we have addition and subtraction. So I make a little pyramid there. That's literally how happened. This is the top dog. You have to listen to him and do all these first. Carry all the instructions that this guy tells you to do first. After you can listen to the lower rank people of multiply and division is the same rank. Addition and subtraction is the same rank. Now, the question arises. When you see an expression, how do you work it out? Alright? So, I want to be very clear about what I tell you now. If when I'm working on a problem, when I work through this phase, after going through this phase, there will be no more brackets and powers seen in the problem. Then I will proceed to do all the multiplications and divisions in the problem. And finally, I'll do all the addition and the subtractions in the problem. Now, I'm going to write a sum on the board. And I want you to understand what's actually taking place. I think it's best shown by an example, so let me do an example. So let's say I have 200 here in brackets divided by 40 plus 16 divided by 2 minus 3 squared minus plus a 3 over 2 all to the square. Alright, let's make it a sum that looks like that. No, let's divide it by something. And divide that now by 4 and a half. Let's say that is a sum. Okay? If you have that as a sum, we're going to work that out. If you know that out as a sum, that's what we do. The question, the rank triangle tells us that brackets and powers have the highest order. So I'm going to put a black bracket around all the brackets and all the powers. Look at power here. Look, a bracket here. And then I said around a mixed number literally has a bracket around it like that. Okay, so I'm going to look at the brackets first. So this sum will be translated into 25 by 40, which is going to be 5. Right back everything that's not in brackets. 16 divided by 2 minus, you have 3 squared, so that actually is going to be and then I'm adding this 3 over 2 squared has to be done first because there's a power, so that means 3 squared is 9 and 2 squared is 4. And all of that is to be divided by 4.5. Oh, but the 4.5 also there's a bracket there, so it's something worked out. 2 4s are 8 and 1 9 over 2. Okay, so all my brackets really have been removed, so I should really leave this out. All of that is divided by 4.5. Okay, so let's see now. All the brackets are taken care of. Look, I'm saying multiplication, I'm saying division. Next thing I have to take care of is the division. So I'll take care of that division now. So I will have now. Okay, so let's see now. All the brackets are taken care of. That line will now become, this is equal to 5 plus 16 5 by 2 is 8. Take away 9 plus 9 and 4. Long vinculum 9 and 2. Now, whenever you see a long vinculum, it means you must work out the entire numerator and then the denominator. So what's actually understood to be happening at this point here is you actually have a bracket here and here. Because this long vinculum tells us work out everything on top, then everything on the bottom, then do your division. Now, in this bracket here, when you look at this bracket, what do we see? In this bracket, in that bracket, you see additions and subtractions only. Now they all of the same rank. Okay? And if these were only additions, as 5 plus 8 instead of minus plus 9 plus 9 and 4, it didn't matter the order in which I added them. I'll get the same result because addition, true and true, is all commutative and associative. But because I have a subtraction there, I have to be very careful which I do my, in the way in which I do my work. So I always start, because all of these have the same order, I work from left to right. Right? So I start from here and I work across gradually. So what I will get is 5 plus 8 is 13. So it's 13 minus 9 plus 9 and 4 all over 9 and 2. And then I have to work out this piece here. Because they're the same rank. So when I go in at the first one I meet, I have to follow. Right, I can't just go and add here. I'm working from left to right. So I'm starting with 13 and then after I have to take away 9 from there. So I'm going to get 4. That's going to be 4 then. That's 9 and 4. I'm sorry, 9 over 2. Because they're the same rank, so I'm going to first one I have to follow. Right, I can't just go and add here. I'm going to come left to right. But the vinculum again says this must be done first. So, using some interesting mathematics, I'll say this is 4 times 1 plus 9 and 4 all over 9 and 2. 1 is 4 and 4, so that's actually 4 into 4 and 4. That's the 1. Plus 9 and 4. All over 9 and 2. So 4 4s are 16, so I get 16 over 4. Plus 9 over 4. And that's what we actually have there. Now because you have a common denominator, we can add the 16 and 9 will get 25 over 4. And this is the vinculum here, all over 9 and 2. And whenever that happens, you divide these two fractions, what you will get is 25 over 4 multiplied by 2 and 9. 2 into 2, 1. 2 into 4, 2. So we will get 25 over 18. The answer is 25 over 18. Okay. So, what I want to do for next day's class, Destiny, I want to take several number 1 questions. Those were the fractions and so on, as I started off with. And you want to make sure you can get it correct perfectly. So much so that you'll be sending me a copy of, let's just take 5 years from now and do number 1A for 5 years, going back from 2018 June, just the June paper, 2018, 2017, 2016, 2015, 2014. Here's the number 1A. We want to perfect our techniques for writing statements. That's what we wish to do. Okay, so I'm now going to take a look at the chat. If there are any things that you don't understand, Destiny, feel free to add it to the chat. Feel free to add it to the chat. Okay, Destiny, so let me just type in something in to make sure that you're with me. Do you follow? Okay, so when you look at the past papers, let me see if I can put up the past papers on the screen. Look at the past papers, all different years. I'm seeing 2018 here, 2018, and I'm going to choose a page, right? All these questions here, you have to know how to work them out, right? So we'll try to do some of these. Just try 5 of them, and just try 5 of them, and we want to work on proper statement presentation, right? We go to this one, I suppose, and right? Just try 5 of these. You don't have to do the part 2 as yet. I'll show you can do that a little later. In 2017. Okay, and you will get okay, so you could look at these. And so on. Alright, so I know you have this book now. Right? You should have this book. And this book starts off looking at some of these questions and so on. So in next class, we're going to look at some of these indices and arithmetical rules and laws and so on and so forth. And we could try some of these questions, right? Right, so I really have this book now. Right, you should have this book. Okay, so and this book starts off. You could pass your person now, but we have this book. I know you should have this book. So we'll start looking at some of the things in this book because we want to get prepared for the exam, you know, as soon as is possible. Alright, so we'll try from 2018 to 5 years, 1 to 2030, yes. We'll try from 2018 to 2030. Let's try that one part with the fractions and so on. And I will show you how best to present the work so you don't make mistakes. Okay, well, since you understand that our time is up, so you have a good night. So tomorrow I think we have chemistry. Okay? Okay, take care.